section 2.4, water is a vital compound. So life here on Earth wouldn't be possible if it wasn't for water. It's the single most outstanding chemical property of water is its ability to form hydrogen bonds. And what are hydrogen bonds? These are going to be weak chemical associations that form between partially negative oxygen atoms and partially positive hydrogen atoms of two water molecules. And so we'll take a look at what exactly that means. But we see here there's frozen water, liquid water, and gas water, or water vapor there. So let's continue here. So the polarity of water. With a water molecule, the bonds between oxygen and hydrogen are highly polar. So oxygen is going to be much more electronegative, which was defined earlier, than the hydrogen atom. So whenever the two bond, the oxygen is going to end up having a partially negative charge. And it's going to be indicated by the lowercase sigma with a positive sign. And the hydrogen is going to have a partially partially negative charge here. Change the ink color here. Okay, so let's say we have a covalent bond forming between one oxygen atom and a hydrogen atom. And what this is saying here is that oxygen is going to have a stronger pull on this pair of electrons than the hydrogen is. So these electrons that are being shared are going to spend more time closer to the oxygen. The result here is there's going to be an unbalanced charge. We're going to have more negative near the oxygen, making it partial negative, and the hydrogen would be a partial positive charge there. So that's for one of the bonds. Now remember, water is H2O, so we have oxygen bound to two hydrogens, so both of those covalent bonds are going to be polar. And the end result here is that the oxygen is going to carry, the oxygen side is going to carry a partial negative, and the hydrogens are going to carry a partial positive charge. Overall, the molecule is balanced in charge. So we look at the entire molecule here, it's balanced in charge, but there's a polarity to it. So if you have two water molecules near each other, then their partial positive negative charges are going to be attracted to each other, and that's what's going to give water a lot of its properties. So here are different models representing the water molecule. I already drew it for you earlier. Here's a Bohr model up on the top left right here, and here you see the partial positive negatives of the hydrogen, and then here's the nucleus of the oxygen with its electrons, partial negative. Here's a ball and stick model, also showing that water has an angle. It's an angular molecule, and then this is a space-filling model. And then we draw our simple structural model that I've drawn before. And so we have our partial negative and partial positive charges there. And so there's our water molecule. So regarding the hydrogen bonds, one of the properties that hydrogen exists is, or that water exists, is cohesion. And here's the polarity of the water allows water molecules to be attracted to one another. So cohesion is when you have similar molecules are attracted to each other. They're said to be the property is said to be cohesion, and this is due to the attraction between the water molecules because of those hydrogen bonds that creates that cohesion. Each individual bond between the water molecules is going to be weak, but if you look at if you sum up all of the effects of every water molecule interacting with the other water molecules, the effects can be huge or enormous. And this is responsible for many of the water's important physical properties that we're going to go over here in a bit. So here is kind of a simple drawing or model showing two space-filling models of water molecules. One water molecule here up at the top, and there's your first water molecule. There's a hydrogen with its partial positive charge, and here's the oxygen, the other one. And the dashed lines are going to indicate the hydrogen bonding, or that attractive force between the two. Here's another case here where we have an organic molecule, where part of the molecule is going to be, this part of the molecule is going to be polar to it. So that would actually attract a polar water molecule. So in this case, this polar molecule, the entire molecule right here, because it's polar, is actually going to be attracted to the water molecule itself that's polar over here. And so this is how water can actually dissolve other molecules that are like it for polar. So something to remember here is that like dissolves like. So if you have other polar type molecules, then water can actually dissolve those types of substances. If the substances are non-polar, which don't have partial positive or negative charges, then water can't dissolve it. So if they're not alike, then we can dissolve the substances together or mix them together. So here's a property of cohesion on the left. You see this insect taking advantage of this property of water, where the insect or the water strider is able to walk on this thin film, or what looks like a film, on top of the water surface. But this is due to the cohesion of the water molecules sticking to each other. This creates what's called a surface tension or a force. And since the water strider is relatively light and has these relatively large feet, it can actually walk on top of the water because of the water molecules sticking to each other, forming this sort of a skin due to the forces between the water molecules. Then here's another property called adhesion. Cohesion is when like molecules are attracted to each other. Adhesion here is when water molecule sticks to other types of polar molecules. And this is what's responsible for, say, water climbing up very thin glass tubing or capillary tubing like you see here. That water can actually climb up it because the water is sticking to the sides of the glass there. So that's called adhesion. Another example would be when you're walking through tall grass, not tall grass, but through wet grass, and it's not that tall. And if you're wearing like cotton jeans or pants, the water tends to run up the pant leg much higher than what the grass was because of the adhesive properties. It turns out that the material, the cotton itself, is also a polar molecule, so the water gets attracted to it and moves upward on your pant leg. So let's take a look at the properties of water, and these properties are due to the polar nature of water. So one of the properties is that water has a very high specific heat. And what a specific heat is the amount of energy that is required to change the temperature of the water. So it requires lots and lots of energy to do that. If you were to take equal masses of water and another substance, like metals don't need to, for example, absorb a lot of heat, and they can change temperature quickly. So if we were to take a kilogram of water and a kilogram of metal, it would take very little heat. You just barely put it on the stove, and that heat and the water temperature, not the water temperature, but the temperature of the metal increases rapidly. But the water has to absorb lots and lots of heat to get those water molecules moving faster, and this is because of the hydrogen bonding. The water molecules basically are being slowed down by their hydrogen bonding, so that energy has to go to help break those or reduce the number of hydrogen bonds being formed. Water also has a high heat of vaporization. Again, this is due to the polar nature of water molecule and the hydrogen bonding there. So here, let's say we get water to a boiling point where it reaches the high temperature and begins to boil. You have to add a lot more heat to get the water molecules to actually break free from each other because of that hydrogen bonding. So that amount of heat is called heat of vaporization, and it's relatively high for water as a substance when you compare it to others. And that's pretty good because that helps water serve as provides cooling. Like when you sweat, you perspire, and the water evaporates off of your skin, it has to take a lot of heat in order to do that, so it can pull the heat away from your body. Water is also, when it becomes solid, when it freezes, it's going to be less dense, and this again is due to not only the shape of the molecule, but its polar nature. When the water molecules freeze in place, they actually freeze further apart. So water is like the only substance that actually expands when it freezes, making it less dense. And so because of this, like in lakes and ponds, when water freezes, it's going to freeze from the top down. And so if it freezes from the top instead of the bottom, then what can happen is you can form a layer of ice on the top, and like an insulation, and underneath fish and other aquatic organisms can actually stay alive in there. This is a model that shows how water is a very good solvent for other polar substances as well as ionic substances. And so this is going to be listed on the next slide, but we can look at it right now. So let's say this is a crystal of sodium chloride right here. Well, the sodium ions are going to have positive charges, and the chloride ions are going to have negative charges. Okay? So what happens here is when you throw a crystal of sodium chloride in the water molecules are going to come and attack these positive and negatively charged ions, and they're going to form these hydration spheres or shells around there. So if water molecules come here and interact with one of the sodium atoms, then the partially negative oxygen side of the water molecule is going to associate with the sodium ion and wrap around it, the way it's done here at the top right there. And then for the chloride, the opposite is true as far as the side of the molecule that associates with the negatively charged chloride ion. In this case, the positively charged hydrogen ions are going to associate and then form a sphere around there. So the result here is that the water molecules actually separate these ions and dissolve them. So this is what happens when you have something like table salt and it dissolves in water. Again, because water is a polar molecule. So that was related here to water being a good solvent. Sometimes we refer to it as a universal solvent because it can dissolve so many different substances, because so many different substances are either going to be polar or ionic, and many polar and ionic substances are capable of dissolving in water because of water's polar nature. So water also can organize nonpolar molecules. So there's two terms here: hydrophilic, these are water-loving, and hydrophobic. I just finished talking about hydrophilic or water-loving substances. They were the two up here: polar molecules and ionic molecules. Many ionic molecules are hydrophilic and they can dissolve in water. But if you're a nonpolar molecule, say like oil or fat, those have no partial positive or negative ends to those molecules. Those are not going to dissolve well in water, so they're referred to as hydrophobic, for phobia, for water fearing. And so whenever you get hydrophobic molecules in water, they're going to tend to stick together with each other and try to move away from the water. So in this sense, the water's polar nature helps to organize these hydrophobic molecules and gets them to group together into specific shapes. We'll see later that's going to be relevant to the cell membranes when we study cells. And then water can also break apart itself, even though it's a polar molecule. The water itself, if I were to draw it down here as a structural formula, H2O is actually structured like this. We can actually break off an OH or a hydrogen from the OH, and the electrons, both of these electrons go this way, and this is going to make a negatively charged group of ions, the OH. It's called the hydroxide ion, which is labeled up here for this ion right here above. Okay. And the other ion is going to be the hydrogen ion, and it's going to be positively charged. Okay. However, when this happens, usually in water, immediately the hydroxide and the hydrogen form or move back together, and so the reverse reaction happens. So this is referred to like a reverse reaction. So at any given moment in time, a very small amount of water molecules in pure water are going to be in this form where they break apart or dissociate, and but they come right back together again, forming back water. But the fact that the water is able to do this gives water some special reactivity where it can become involved in reactions itself. And a great example is with acids and bases. So let's take a look here. and briefly define acids and bases. We'll learn more about acids and bases in the laboratory. But pure water itself has, and this symbol right here, anytime you put brackets, this is going to be referred to the concentration of a substance. So I have X in brackets here is going to be referred to what's called the molar concentration. And it's just a way of measuring how much of a substance you have dissolved in the solution. The greater that number, the greater the concentration. So in this case, this would be the molar concentration of X. So when you see it here, this would be the molar concentration of H pluses, or hydrogen ions in there. So in pure water is going to have a concentration of 10 to the negative 7 moles per liter. It's a small amount, but we were talking earlier about how water, I'm going to drop here at the top, water can dissociate into the hydrogen ions and the hydroxide ions. So when we have pure water, when pure water dissociates relative to the amount of water, the concentration of the hydrogen is going to be a very, very small amount. When we say 10 to the negative 7, that's a small number. That's saying 0.00000123456 and then 1. So, and then that would be saying moles for every liter of water. So very, very far from 1 mole per liter of water. We're talking about 1/10 billionths of a mole per liter. But still, it's a small and measurable amount. When water has this concentration of hydrogen ions, it's considered to be neutral, and we would call it a pH of 7. And this is neither going to be acidic nor basic. So this brings up the idea of pH and what is pH. So pH then is, it says it's the negative logarithm of the hydrogen ion concentration. So pH then is, which is equals the negative log of the hydrogen ion concentration. Okay, so we said in pure water is 10 to the negative 7 moles per liter. So pure water would then be negative log of 10 to the negative 7. Okay, that answer we're going to get is 7. And so it might be good to pause here for a bit and define what a logarithm is, especially logarithms when they're a base of 10. So anytime you have a logarithm, basically, or a common log, which is log with a base of 10, is saying that the log of that number, so the log of 10 raised to some power n, is basically, the answer is going to be the exponent. Okay? So if we were to take log of 10 to the 6th power, then the answer would be 6. Okay? So log of 10 to the 6th. If we were to take log of 10 to the 2, the answer would be 2. By the way, 10 to the 2 is the same as 100, so the log of 100, the answer is 2. It's the same, because 10 to the 2 is 10 to the 100. So if we have a small number, say log of, like we said up here, 10 to the negative 7, when we're talking about the concentration of hydrogen ions. So the log then of 10 to the negative 7, well, the answer is supposed to be the exponent, which is negative 7. Okay, so we're talking about the pH of pure water. Concentration of hydrogen ions is 10 to the negative 7. So when we plug that in there, if we don't have this negative sign, the formula does have a negative sign right there. Okay, if we don't have the negative sign, then the answer should be negative 7. But what does the negative sign in front do? It says change the sign. So basically that changes the sign, making it a positive 7. Okay, so a pH of 7 really is saying that the concentration of hydrogen ions is 10 to the negative 7. If we have a pH of 6, then the concentration is 10 to the negative 6, which is actually going to be bigger. Okay, so that's kind of how this equation works here. So this is kind of a handy equation to remember, and it will be helpful to remember what the answer of a log means, the exponent. Okay, whenever we're taking a base of 10, log of some base 10 of some number. Okay. So let's looking at acids a little more closely here. For acids and bases, an acid, what is it anyway? It's going to be any substance that dissolves in water to increase. Remember the symbol here? It means hydrogen ion concentration. And when that happens, it's going to actually lower the pH. So we're going to go from 7 neutral, and we're going to go somewhere lower than that. Because the lower the number, the higher the actual value is going to be. So remember, the pH of 7 is the same as saying 10 to the negative 7 when it's on the pH scale. A pH of 6 is the same as saying 10 to the negative 6. If we get it low enough to where we have a pH of 2, 2 is the same as saying concentration of 10 to the negative 2. 10 to the negative 2 is a lot bigger than 10 to the negative 7. So basically, the more hydrogen we add, the lower the pH will be, because we're going to have a higher pH concentration. Okay? So the stronger the acid is, if it's stronger, the more hydrogen ions it produces and the lower the pH. I'll give you an example of a very common laboratory acid. It's called, it comes from a substance called hydrogen chloride. It's a gas at room temperature. And if we were to dissolve it in water, okay, so if we dissolve it in water, as the hydrogen chloride dissolves in water, say we put bubbles of this gas in the water, and it starts to dissolve, we put G for gas, it's going to break apart or dissociate, and it's going to produce hydrogen ions, and they're going to be dissolved in water, so we're going to say AQ for aqueous, which means in water, and the chloride ions are also going to be aqueous as well. But what if we increase by dissolving that in the water? We're going to increase the amount of hydrogen ions. So what does that end up doing? Lowering the pH. Okay? A base, on the other hand, is a substance that combines with the hydrogen ions dissolved in water, which ends up lowering the hydrogen ion concentration. Okay? Remember the brackets with the hydrogen ions. Well, the hydrogen ion means concentration, molar concentration. But basically, any base is going to be a substance that if there's free hydrogen, that base picks them up. So we can think of a base as a hydrogen ion acceptor. And sometimes they call hydrogen ions protons. So sometimes you'll hear me refer to hydrogen ion as the same thing as saying a proton. Well, why? Because a hydrogen atom without its electron is a proton by itself. Okay? A great example of a common laboratory base is sodium hydroxide. And it's solid. You can buy it, it'll be in solid chips. And if you dissolve it in water and it becomes aqueous, you're going to get sodium ions, and they're aqueous, and that releases hydroxide ions. And hydroxide is a fairly strong base. Whenever hydroxide is present, it's going to pick up the hydrogen ions, which, by the way, the hydroxide with the hydrogen is going to form water. OH is the same as H2O, H2O water. So anytime you put the OH in there and there's free hydrogen ions, they combine to form water on there. So again, what is a base? A base is going to be something that when it dissolves in water is going to accept or pick up these protons or these hydrogen ions from the water. And so what does that do? That takes the pH and changes it in the other direction. It increases the pH. And so if we're increasing the pH, let's say we start at 2 and we add a base, the concentration is 10 to the negative 2 moles per liter, which we see up here at the top, right? If we start increasing, we go from 2 to 6. We go from pH of 2 to 6. Well, now we have even less, because 10 to the negative 6 is a lot smaller number than 10 to the negative 2. And 7, and then so on. Okay? So let's take a look at the pH scale here. And so here we have the pH scale. The pH value in the middle is neutral, right there. Pure water is neutral at a pH of 7. Remember from the previous slide, pH of 10 to the negative 7, or a pH of 7 is the same as having a hydrogen ion concentration of 10 to the negative 7. Remember the formula? pH equals the negative logarithm of the hydrogen ion concentration. So here, all of these are the actual concentrations, the hydrogen ion concentrations. If we were to put those numbers, these values, like say we put 10 to the negative 5 in here and we plugged it into this equation here, we're going to get an answer of 5, because remember the log is the answer is the exponent, but then the negative is going to make it positive. So the exponent here is -5, so our answer is going to be -5, and then we have to change the sign to +5. So there's your +5 pH. And so the lower we go on the pH scale, the more acidic we're going to be, because we're getting higher and higher hydrogen ion concentration. So I'm going to put a line like this here and say increasing. Okay. And then we can compare the pHs to some common substances. There's that laboratory balance acid I told you about, hydrochloric acid. In your stomach has a pH of 2. That's relatively strong acid. Lemons, vinegar, soda, and beer have a pH around 3. Tomatoes of 4. All of these are acid. Anything lower than 7 on the pH scale is an acid. Urine is slightly acidic, so is coffee. If we start going higher in pH, higher in pH means we're having a bigger and bigger negative exponent, and the bigger that negative exponent is, the more zeros between the decimals, so it's a lot smaller. So going to pH 8, 9, 10, 11, 12, 13, 14 is going more and more basic. Okay, and we go to that strongest, that laboratory acid I mentioned. There's your sodium hydroxide here. Bleach is a base. Household ammonia. Baking soda is basic. Seawater is slightly basic at a pH of 8. So pH is fairly important there. So regarding pH is a lot of times living things need to fight to keep pH from changing too much. For example, in your blood, you have to maintain a certain blood pH. Otherwise, if you don't, then things are going to start happening because your pH is not in balance. So we'll constantly have to have a balanced pH. Okay. So we do have substances that guard against significant changes. So let's say for some reason a process within your body is producing a lot of hydrogen ions, the reactions are, and so what's going to happen is you're going to have a way of protecting against having a big change. And one of those protections includes the concept of buffers. Buffers are going to be substances that help resist or prevent significant changes in pH regardless of the amount of hydrogen. Now the system can become overwhelmed if you put too much hydrogen is formed, hydrogen ions, but overall the buffers help to reduce that. So how do these buffers work? These buffers are going to act by releasing hydrogen ions when a base is added. So let's say the solution, you add base to it, the pH should change to a higher pH. But what's going to happen here is that the buffer will release hydrogen ions, and those hydrogen ions are going to combine with whatever base is being released. So when they combine, then we're going to end up removing that base from the solution, so it becomes attached there, and then you reduce that base from the system. So the other thing it can absorb hydrogen ions when an acid is added. So if you have acid being added, then the buffer can absorb the hydrogen ions that are being released. So what is the overall effect here? It's going to keep the hydrogen ion concentration relatively constant in this case. Okay? And so this shows the effect here. So what we have here is our pH on this scale here. And we start at 0 and we go up to 9. Okay, so there's your pH. And then over here is what we have on this scale here is the amount of base added. So here is 1 times the amount of base, and then if we double the amount of base, we add triple, quadruple, and so on. And so let's say to our solution, we start off slightly acid, and we have a buffer in it, right? So we have a buffer in there. If we start adding a base to it, then we should see this linear, I'm going to draw that here, this linear or this increased as we add more and more of the base. We should see this linear increase in the pH. But we don't see that because we're going to have a substance in there that as you begin to add more and more base, that base is going to be picked up by the buffer. When the base is added, that buffer is going to be releasing hydrogen ions into the solution. And so the hydrogen ions are going to combine with the base and basically prevent the pH from going too high. So here we're adding base, the pH begins to rise, and then the buffer begins to become active. And so what happens here is we level off. And so we have relatively little change in our pH. Eventually you're going to overwhelm the system though, and if your buffer runs out, then as you continue to add more and more base, then all of a sudden there goes your pH, and your pH begins to increase further. So there's going to be a certain range within which your buffer can do the job, and then you overwhelm and you put too much in there. So that's the case. So a good example of a biological buffer that we have in our blood, for example, is the carbonic acid bicarbonate buffering system here. So the way we get carbonic acid in our system is when carbon dioxide dissolves in your blood plasma, it's going to react with the water, and it produces this carbonic acid. So H2O plus carbon dioxide here produces this H2CO3. There's your carbonic acid. It's a relatively weak acid. I'm going to draw up here the H2CO3. When it does dissolve, so it'll dissolve in water, some of it, a little amount, is going to release one of the hydrogens. So there's your hydrogen being released, okay? And it's going to produce the bicarbonate ion, which is one less hydrogen, CO3, and it's going to have a negative charge to it, okay? So that's this molecule right here, bicarbonate ion, and then there's your hydrogen ion, okay? And this action is reversible. So I would say for this system here, we just put some regular carbonic acid in the water. Maybe about 1 out of every 20 of these molecules dissolves to form this, right? So let's say now we have this in solution and it's in equilibrium. We have a certain amount of carbonic acid and a certain amount of hydrogen and bicarbonate. If I were to add a base to the system, let's say I add hydroxide, which is a strong base. What's going to happen here is this hydroxide is going to combine with the hydrogen, so the hydrogen gets removed. What ends up happening is another carbonic acid molecule moves in this direction, so it breaks apart. And then that hydrogen that it leaves can pick up another hydroxide. So as we continue to add more and more base, this equation will shift to the right. It'll move to the right to release hydrogen ions, like it did on the previous page. So those hydrogen ions pick up the base. Okay. Now let's say we pick up alternatively, instead of throwing a base in there, we throw an acid in there, right? So now we begin to release hydrogen ions. We're adding hydrogen ions. That's going to increase in the system. As we add more hydrogen ions, there's only a certain amount of this that can exist on its own in the solution. So when we begin to add more hydrogen ions, what's going to happen is the hydrogen ions are going to combine with the bicarbonate and reverse the reaction the other way. So this then, the bicarbonate, acts as a base to pick up the extra hydrogens that we're putting in there, and it shifts the reaction back to the left. So what does that do? That helps reduce the amount of free hydrogen ions in there as you're adding more. So this system can go either way depending on if you're adding a base or if you're adding an acid. And the overall effect here is that the buffer prevents pH from changing significantly. So there's your buffers there. And that sort of does it, but I do have a quick question here. If we do the pH, something to think about. So let's say we have here a pH. I'm going to draw the scale. Over here is pH of 0, and over here is pH of 14. This is neutral. This is acid, and over here is base. Okay. Neutral. So my question here is, if you add an acid, which is going to increase the hydrogen ion concentration, it should go lower. So let's say we go from a pH of 7, we go to 6, we keep adding acid, we go to a pH of 5. Okay. My question is, by how much does the hydrogen ion concentration increase? Okay. It's going to increase when you're going in this direction. So that's going to be, we'll say that direction is increasing hydrogen ion concentration. The opposite would be decreasing in the opposite direction. So if we add acid to a neutral solution and we go from a pH of 7 to a pH of 5, the question is, by how much does the concentration change? Many students will be tempted to say it changes by 2 units because we go from 7 to 5. But remember, this is a log scale, which means every jump in pH, a pH unit is a 10 times change, or a 10-fold increase. So if we go from 7 to 6, it's really we're going from 10 to the negative 7 hydrogen ion moles per liter to 10 to the negative 6. That's a tenfold change. And then if we go from 6 to 5, we're going from 10 to the negative 6 to 10 to the negative 5. That's another tenfold increase. So really it's going to be 10 times 10. So it's 100 times change. So each step is a factor of 10. Okay. Now if we were to go the other direction, okay, let's say we go from a pH of 5 and we add base. We're going to go in the opposite direction. pH is going to increase. And we go from 5 to 7. It again is a change of 100 times, but we're going 100 times smaller, or 1 over 100 fold change in the hydrogen ion concentration. And let's say we start at a pH of 7 and we add base. So we start out neutral, we add base, and we go to a pH of 8. And I ask, by how much does the hydrogen ion concentration change? Students may be tempted to say, well, it changed by 1 unit. It changed from 7 to 8, so it's 1 time. It changed by 1 unit. The correct answer here would be that it changed by a factor of 10, and it's 10 times smaller. You can also say 1 over 10. It changed by a factor of 1/10 because it's a tenth smaller, because we're going from 10 to the negative 7 to 10 to the negative 8. So be aware of that. Every time we move a step on the pH scale, you're changing by factors of 10. Either 10 greater going to the left, each step 10 factor of 10 greater, and each step factors of 10 smaller. Okay, so keep that in mind.